Thanks. Yeah, all right, so today I'm going to discuss my most recent paper, which is submitted and should be available tonight on archive, though I've been having some trouble with the archive part of this. But anyway, this paper is about the electric field screening of pair discharges and generation of pulsar radio emission. So the motivation here is likely familiar to most people. Pulsars are observed to emit coherently and radio from the polar path of the pulsar. So on the left side of the slide, you see an artist's depiction of a pulsar. You can see the magnetosphere traced out by these light blue lines. And then at the poles of the magnetosphere, you have this light purple glow, which is indicative of the radio emission that we observe from pulsars. This has been known about for quite a while, but there's some aspects of this emission that remain unexplained. One of them is why the luminosity is what it is. So on the left, you have a plot from a set of observations where along the x-axis you have the pulsar spin down luminosity, and along the y-axis you have the radio luminosity. The different types of points are different types of pulsars, and the lines are in a fit that the observer wanted to do, but it's not important to us today. And you can see that this radio luminosity has a magnitude of roughly 10 to the 27th to 10 to the 31st ergs per second, and it's not really clear why that should be. Another aspect of the radio emission that people are interested in understanding is the spectrum. So on the left side of this slide, you see an observation of one particular pulsar, where along the x-axis you have the frequency of the emission that's being observed, and along the y-axis you have the energy at that frequency. And you can see that this pulsar has a spectrum with an index of roughly -1.4. There's a lot of scatter in what spectral index is across many different pulsars, but this one is sort of an average pulsar, you can say. Because if you look at a set of different pulsar observations and you combine them all, you find that a typical spectrum is what's given in the light green box at the right. So you can see this goes like frequency to the -1.4 with a big scatter on top of it. And again, it's not really clear why this spectrum should be as it is.
So in like the last slide for this one, so the line below it is what you predict. Like you said, I mean, this cannot be explained, but how well can this be explained? Like to what degree?
Well, right. So the line, which line are you asking about?
I thought like one of them was predictions, one of them was observations. Is that?
Oh no. So these dashed lines are just some sort of fit that somebody wanted to do. There's no meaning to it. I would have removed that from the slide if that had been my slide. Yeah, my understanding is there's not really a good understanding of why this luminosity is what it is. So
can we explain like we can explain like a fraction of it, but not the whole thing.
Well, right. In this project, actually, we advanced potential explanation for why this luminosity is what it is. This is one of the motivations for undertaking this project. You know, is what we come up with correct? I don't know.
Yeah. Is it specific for like certain type of pulsars? Like, does it exclude any second pulsar, or it just includes all the pulsars?
Yeah, I'm not a super big expert on millisecond pulsars, so I'm not sure what the situation is there. But for normal pulsars, this is pretty typical. All right. So I'm a plasma physicist. So these are characteristics of the pulsar that arise from the plasma physics. So I was, interested in looking at why this might come about and looking at the plasma physics behind it. So in this talk, we'll talk about the plasma physics of this process in two parts. First, we'll talk about the polar cap discharge, where the radio emission might be produced through screening of an electric field that exists near the pulsar. And then we'll discuss the three important stages of electric field evolution of the polar cap discharge with implications for observation of each. So there's going to be a screening phase, there's going to be a nonlinear phase, and then there's going to be a linear phase. All right, so to understand the nature of this radio emission, we have to zoom in on the polar cap region. And if you do that, what you find is actually somewhat complicated. So if I, follow the yellow line, you find that in this polar cap of the pulsar, they've got a very strong inductive electric field that results from the pulsar's rotation. And this inductive electric field basically creates this paired discharge, which fills a magnetosphere with plasma. The nature of this discharge is quite complicated. You can see a diagram from a paper looking at the discharge in detail in 2015 on the left of the slide. So there's really a lot of different physics going on there. But for purposes of the talk today, we can take a simplified model of the discharge, right? So if we zoom in on the polar cap region, where here this orange is again the neutron star surface, you see the blue lines of the magnetic field of the pulsar magnetosphere, and you've got the strong electric field pointing in towards the surface of the neutron star. So this strong electric field will basically extract electrons from the surface of the neutron star, and it'll accelerate them to a very high Lorentz factor, roughly 10 to the 7th. So these electrons are moving along curved magnetic field lines. So what happens is they actually radiate gamma rays through a process called curvature radiation. These gamma rays are subsequently absorbed in the magnetic field, and a QED process will create lower energy pairs of a Lorentz factor of roughly 10 to the 2. So, right, in this process, it's important to note that the primary population of electrons is at such a high Lorentz factor that it can't really interact very strongly with the electric field. Its interaction is very suppressed. So the primary population of electrons will sort of continue to exist in a cloud of paraplasma that's moving away from the star. And as it continues to exist, it will continually see this QED process. So you'll get continual creation of the lower energy pairs. So these lower energy pairs are not as energetic, so they are able to interact with the electric field, and they screen out the electric field. And they'll set up waves, which might become the radio emission, right? So these waves will be generated by the secondary pairs, and then they'll also evolve due to the continual addition of more secondary pairs. So the idea that this might be responsible for radio emission has been sort of a topic of interest recently in several papers, including the one that I cite here. All right, so this is a two-dimensional process that happens in the polar cap. So if you simulate what's happening in this discharge using the simplified model that we discussed previously, you get something like what you see on the left side of the slide. So here up at the top, you've got the same neutron star surface, and then you've got a coordinate system here. And basically, you get the creation of a plasma cloud. You see in this first plot of the plasma density. Right, I don't know if you can see my cursor or not, but anyway, that is a cloud of the primary and secondary pairs that are shielding out the electric field. So as they shield out the initial electric field, they're going to set up plasma waves that have a component which is an oscillating electric field, and it's also going to have a component that's an oscillating magnetic field. So together, this oscillating electric and magnetic field will create a pointing flux, which you can see in the final image on the left. And this pointing flux is what can actually escape the polar cap region as the radio emission that you observe. So this is a complicated two-dimensional process, but we're really interested in sort of zeroing in on what's important about the interaction between the waves and the radio emission that you observe. And it turns out that what's important is the parallel dynamics, right? So the pairs in this process are going to move only along the magnetic field, which is in the x direction in the plots that I've shown here. Right, because they can't move across it. And so the pairs are going to interact with these waves through the parallel electric field, which is also in the x direction in this plot, right? So you can see from Ampere's law, you get the time dynamics of this process are really governed by the parallel dynamics along the magnetic field. So this means that we can look at the evolution of the radiation amplitude by just looking at a one-dimensional process, which is slightly different from what's going on here, but will give us the keys of the physics. So this is the interaction of a parallel electric field with newly created pairs. Right? Yeah. Oh.
What's ensuring the coherency in the radiation that you get there?
What do you mean by the coherency?
Like if you get all of those waves, why don't they destructively interact? But you get coherent.
I'm not sure why they would interfere necessarily. You have a bunch of different modes that are moving superluminally, and they just all sort of go out of the plasma. I'm not sure what the interference process would be, but actually this would be a good thing to discuss further. All right, so basically
the emitted light is in radius because it's the oscillation frequency or something.
Yeah, it's the oscillation frequency, basically of the plasma wave, and that it gets modified slightly as it leaves the plasma, but it's a non-major modification, shall we say. All right, so basically I'm going to take a simplified version of this problem. So you have this complicated discharge, and you're going to just sort of follow the purple arrow, and instead I'll look at a case where you have a strong electric field. You don't need the magnetic field because particles are just moving along it and they don't feel it. And then in the strong electric field, you can inject sort of by hand, or just say that there's some injection rate of secondary pairs like this. Right, so we can look at how this process would occur in a PIC simulation. And in particular, we can look at a simulation where you have a vacuum electric field, which is continuously created Lorentz vector of 10 pairs with a slight temperature spread. And we can see that process in a PIC simulation on the right side of the slide. So this is a normalized root mean square electric field in a simulation box, but basically you just have an electric field there, and that's how big it is. And you have normalized time along the x-axis. You start out with a strong electric field up here in the pink. And then if you look at the second plot, as time goes on, you just add more pairs to this electric field, and you show, and this electric field starts to oscillate and starts to get smaller in magnitude as you add more and more pairs to the process. So our work is building analytical models of the screening and damping process and comparing them to PIC simulations. By doing this, we're able to give some insight into the luminosity and also the spectrum of the pulsar. And I'll note that I come from a background looking at basically laboratory plasmas and tokamaks. And so in this project, we took a lot of inspiration from physics that's used in tokamaks to describe how plasma is heated by plasma waves. It's a bit different in this context, but there's some parallels as well. So looking at this process, we find that the electric field damping actually has 4 phases. One of these will turn out to not be important, so that's why I told you there were 3 at the beginning. So here I have just the same electric field evolution that we had before, and I've identified 4 different phases on it. So the first phase is a screening phase. This is when the initial electric field is shielded out. Then we have a second phase, which is a nonlinear phase. So this phase sees very strong reduction in the amplitude of the oscillations. And this phase is going to have physics where pairs that are newly added to the discharge are fully reversed by the electric field, right? So if we look at the electric field again in pink on the right, if you put new pairs in it moving at some velocity, these will get fully turned around. If they're one sign, and the other sign will get, dramatically accelerated in the other direction. After that, we have a third phase, which I'll just call the frozen phase. This is a phase, is an artifact basically of the simplified setup we use in our simulation. And it eventually ends due to sort of some breakup of the waves that are existing in our simulation. But this is basically an artifact of our simplified setup, and it's not expected to occur in the 2D setup. But we do discuss it in our paper. Then after that, we'll have a phase with linear waves and weak damping. So the physics in this phase is that pairs newly added to the electric field are not fully reversed by the electric field, right? So they get their velocity changed a little bit, as you can see by the change in the arrow length, but not very much. All right, so we want to do analytics here. So to do that, we have to know what equations we're going to solve. So these equations are familiar to people who are plasma physicists and perhaps totally baffling to people who are not, but that's okay. So basically, we have our Vlasov equation, our Ampere's law, and a definition of a current. So in all these equations, I've taken basically normalizations that are appropriate to the problem. You can see the definitions of these normalizations in the box with the purple heading at the right of the slide, but you don't really have to worry about that if you don't care about it. So the Vlasov equation is basically going to relate the time derivative of your normalized distribution function, the strength of the electric field and the particle charge, derivative with respect to momentum. And then on the right side of it, I'm going to add a source term, which is representing the addition of new pairs at some momentum UL to the system. Then I have an Ampere's law. And because of the normalizations that I've taken, you have this factor gamma, which appears in the Ampere's law. And then the final equation is just a definition of a normalized current. So that's not super interesting. So if we look at these equations, there's really only two parameters in them. The first is this UL, which is the momentum of the freshly created pairs. This presentation simulation that has a value of 10, but in an actual pulsar, it can be quite a bit higher, up to about 1,000. And then we have this parameter gamma, and this is relating the energy in the initial electric field to the energy created in energy in pairs that are injected in a specific unit of time. So if you work out how strong this would be in an actual pulsar, you can find the scaling at the right of the bottom of the slide. So basically, this is quite a large number. It increases with the magnetic field strength of the pulsar, decreases with multiplicity, and decreases with period. In the simulation results that I'll show, we take a small value of it, so that just makes the simulations run faster. But basically, we work out how everything scales with this parameter. All right, so I can also combine the previous equations to get an equation for the evolution of the electric field in terms of a relativistic plasma frequency. So this is likely familiar again to people who are plasma physicists, but baffling to everyone else. But basically, you have a second derivative of the electric field. You've got some frequency, and then you've got the electric field again. You can see the definition of the frequency in the second yellow box, right? So this depends on the density of the positrons, the density of the electrons, and the average value of 1 over Lorentz factor cubed in each of these populations. All right, great. So these are the equations that we're interested in solving to understand the pulsar radio emission. So now we can look at how this physics behaves in each of the phases that we've identified previously in, yeah.
I wanted to ask what's gamma, but that suddenly appears on the screen, sorry.
Oh, yeah. So this is, right, it's just because of how I've normalized the equations, basically. So it's just telling you basically the relationship between the strength of the electric field you have to screen out and how good you're doing at screening it.
Well, what's the definition is going to be in the next slide.
Oh, right, so it comes out just from the normalization of your equations. But then if you
cut off on the screen.
oh
Gamma equals.
Oh my gosh, this is
probably yes.
bad actually. You're missing like an inch on the side of the screen.
So it's gamma, which is defined at the bottom, right?
Yeah.
Okay.
Well, but this is not gonna be great for the rest of the presentation. This is better, right? If I can zoom in on it. Is that going to be better? Do people prefer that? Or not?
I mean, we can see all the edges, but if you zoom in even more, might be better.
Yeah, because I don't think it's going to be great with the left side.
Yeah, that's good.
That's fine. That's
yeah, great. Okay, right. So, So the definition of gamma is down below, right? All right. So during the initial screening phase, we're just shielding out the initial electric field. And during this phase, the pairs that you add to the discharge are basically totally torn apart, and they fly off at exactly C in both directions. Well, not exactly C, obviously, but very close to it. And by making this approximation, you can find that the electric field is screened in a time that goes like the square root of gamma. So basically, if you think about how this physics would occur in the polar cap discharge, it makes a lot of sense. In a stronger magnetic field pulsar, you have more energy in the initial electric field. So it takes longer to screen, so the screening time is higher. You have a higher multiplicity, pairs are being injected more quickly. So it's a shorter time to screen. And if you have a higher period, there's less energy in the initial electric field, so it's shorter to screen. All right, so in this process, you're gonna also accelerate your pairs that have been added, right? And if you take a model for the electric field evolution in this stage, you can use it to solve the Vlasov equation and get a distribution function for the pairs that results from this process. So you can see that in the plot in the middle of the page. So you have, this is the positron distribution function, and you have the momentum here, and then you've got the distribution function here from simulation in red and from analytics in blue. The blue line is a little bit light, but they do agree. So if you want to think about what the observational consequences of this particular stage is, so some of these pairs that have been reversed will actually kind of leave the cloud of plasma that you're interested in, and they'll slam into the pulsar surface. And this can create the hotspots that are observed by NICER. So sometimes when people study these hotspots, they need some sort of model for what the spectrum of particles that hits the neutron star is, and you could potentially use this distribution function as a model for that. All right, so after that, we're going to enter our nonlinear stage marked by strong damping. So here on the bottom left of the slide, I'm going to plot basically the value of the normalized electric field, it's amplitude, right? So you can see it starts negative and then goes like that. And if we want to know how this electric field evolves, we return to our equation in blue. And to understand this, we clearly need to know what the frequency is doing, which I've repeated in this yellow box. And if we look at the frequency during this phase of the discharge, we see that it has these weird spikes, right? So it's quite small, and then it gets pulled up like this, and then goes down and up and down. So this is clearly the dominant behavior in the frequency during this stage, and it's what's going to basically determine how the electric field is evolving. So let's kind of think about this spiking and what it might mean. Right. So I'm to do this, to understand how the average Lorentz factor and the distribution evolves, we have to know what the distribution function is doing, right? So I can take the electric field evolution that we've had before, and I can look at a particular balance of the electric field in the nonlinear stage. And I can provide you all with a video of the electron distribution function in that time period. It's the one that's not sort of blurred out by these brown boxes, right? So I'll just play this through once and then we'll discuss it, right? So just show it once and then we'll show it several times again. So you've got the momentum along the x-axis and then you've got the electron distribution function. And I've called out the pair injection momentum with the blue arrow. Okay. All right, so the rest of this video is less interesting. Well, actually, we'll talk about it later, right? But all right, so the initial formation of the spike is happening right about here. So basically, the physics of what's going on here is when we're starting the video, the electric field is near zero. So pairs that you add, you drop in at a momentum of 10, they're not going to get pulled in any direction, and they're basically just going to build up in phase space, right? And the electric field is very low. So you see this formation of a big bump in the distribution function. That's when you're just adding more and more pairs that are not getting moved to other momentum. But so you've got this big bump, and then the electric field will increase, and this will start to pull the bump. You can see this thing really starts to move as the electric field picks up, right? But you've got this big bump of pairs, right? And they're going to get pulled through a momentum of 0 as they're reversed. So this is a Lorentz factor of 1, right? Which is much smaller than the other Lorentz factors in this situation, right? So as you pull them through Lorentz factor of 1, the average value of 1 over Lorentz factor cubed and the distribution function is going to get much larger. So that's what is causing these spikes here, right? You have a bunch of pairs being pulled through a low Lorentz factor, and then they're pulled out of it, right? So being pulled into it pulls the spike up, and being pulled out of it pulls it down. Right, so that's what's causing these spikes in the frequency. Now, all right, it's also somewhat interesting to know how the full distribution function evolves over the course of this nonlinear bounce, even after the spike. Let's see.
What exactly sets the period spikes?
The period, right? So that's going to be, so that's basically like the duration of each bounce of the electric field, right? So that's right. So that's determined by a couple different things. One of them is just, you know, the plasma frequency away from the spikes, right? So that depends on like how much density you have there. That's the main part of it. All right, so we can also sort of zoom out in phase space and look at how these overall pairs behave during this bounce of the electric field. This doesn't really have any physics consequences, but it looks kind of neat. The developer of the PIC code that we used, he thought he liked this distribution function. He compared it to a wave foam. So you can see our bump from before is getting pulled way out, and then as the electric field is going through zero again, or as it's getting smaller again, you're going to get another bump. And right, so this bump will just get pulled the other way, but the other sign of charge will have the same process that you have in the sign of charge. So you get this continual formation of the spikes. All right, any other questions at this point? All right, so, okay, all right, I saw a hint. All right, so now we know what's going on in the frequency, and we want to know how that's going to affect the amplitude of the electric field. So you can look at this from a mathematical point of view or from a physical point of view. So we'll start with the mathematical point of view. So here I'm going to zoom in on the plot we had previously, and I'm going to call the time at which the electric field goes through zero, capital T naught hat. So we're, you know, again, always concerned with this yellow equation. And we need some sort of understanding of what this frequency does. So I can take a simplified model of the frequency, where I can just represent these spikes as delta functions, right? They've got some width, but just, you know, you can build that into your delta function model actually. So you just think about them as having a spike at one period of time. So these spikes are slightly offset from the times that the electric field goes through zero. The offset can be represented by a small parameter delta. So to see how the electric field behaves, we can integrate this equation. Right. And if you integrate this equation, you find what is given in the second yellow box. So here, you have the derivative of the electric field at a point after the spike, basically in orange. You can relate that to the derivative of the electric field before the spike, and also the value of the electric field at the point of the spike, right? So basically, what's happening here is you've got a positive electric field after the point of zero. So this is going to take the derivative of the electric field and it's going to pull it down, right? So you've got an initial green derivative, and then it's going to become orange. So this is a reduced derivative, and that means that the electric field amplitude in the second bounce is going to be smaller. This will correspond to damping, right? Because it can't go up as much because the derivative is smaller. Right, so that's the mathematical source of this behavior. We can also consider what the physical mechanism here is. Basically, the physical mechanism is the reversal of the newly added pairs, as I've said before. But basically what happens is when you add new pairs at this stage of the discharge, they really get sort of torn apart by this electric field. And that's a very violent behavior that takes a lot of energy out of the electric field. And taking energy out of the electric field will correspond to damping the electric field. Makes sense to everyone. Great. So this Damping can actually be modeled analytically in more detail if you're curious about this. We discussed this in our paper, but just to give you sort of a highlight of the results, you have the nature of the electric field, so you can analytically solve the Vlasov equation for such a field to see how the pair distribution function changes, right? So you can see the results of that on the left. So you've got momentum here, you've got distribution function along the y-axis. And you can see simulation data and also an analytic solution for what the distribution function should be. And they roughly agree. The disagreement is because this orange is not, considering pairs left over from very early in the discharge. So when you have this analytic solution, you can use it to numerically solve for the average 1 over Lorentz factor cubed and the distribution function. And from there, you can actually work out expression for how the electric field amplitude is going to damp during this phase. You see that the amplitude will reduce exponentially. So this is very strong damping with a strength that depends on this gamma parameter. And this agrees with the observed damping of the electric field in the simulation. So, okay. All right. Right, so we can pull up our definition of gamma again, and we can look at the strength of the nonlinear damping in this phase. And we show that we can see that it's weaker for higher magnetic field. This is because there's a higher magnetic field pulsar, you're having more energy in the initial electric field, so it's harder to damp. It's stronger for higher multiplicity. That's because you've got more pairs injected, so it damps a lot faster. And it's stronger for higher period, less energy in the initial electric field. So I say on the slide that this stage has unclear observational consequences. The main consequence of this stage is basically that this damping is incredibly strong in all pulsars, right? So this electric field is going to get reduced very quickly, and the amplitude of the fluctuations that get escaped as radio emission will also decrease very quickly. And so basically the main consequence here is that this phase will complete in all pulsars that you could conceive of, right? So the emission that you see will be way past this phase when it escapes, and you won't have any way of seeing an effect of this phase. Right. All right. Right, so this phase is very strong damping, but it doesn't go on forever. It's not like it takes the electric field completely away. In particular, it seems to stop at a certain point. So on this slide, I can look at the evolution of the electric field as a function of time, right? You can do an exponential fit. This is a fit from the strength that we've, well, actually, I think this is not. This is a damping of the strength that we've estimated previously, and it does really well, and then it stops doing well. So the question is, why does this exponential damping seem to stop? Right. Okay, so we'll say for the 3000th time that this damping is caused by the electric field pulling pairs injected at momentum of 10 through a Lorentz factor of 1. And this damping won't work if you're not able to pull these newly added pairs through such a low Lorentz factor, right? So if you look at how much momentum an electric field in an oscillation can give to a particle that's participating in that oscillation, it's given by the value of the electric field strength. All right, so okay, here I've called an amplitude of the star. So it's given by the electric field amplitude over the frequency. So if you're a plasma physicist, you may know this parameter as a quiver velocity, a jitter velocity, or a Wiggler A parameter. It has different names and different subfields. But basically, this is the amount of velocity or momentum response that you have. Right. So in the non-relativistic case, it's a velocity response. Here it's a momentum response that's resulting from a specific amplitude of the electric field. So we can plot this out in our simulation at the bottom left of the plot. So you've got along the x-axis time, along the y-axis, this quiver velocity, right? And initially, the electric field is very strong. So the change in the pair momentum, I should say quiver momentum, change in the pair momentum is very, very strong initially, right? So this is really tearing these pairs away from their initial injected momentum. But as the wave damps, the amount of momentum change that you can get from the wave is going to get smaller, right? And at a certain point, it will get to be equal to the injection momentum of the pairs themselves. So at this point, the wave is not strong enough to reverse these pairs. It's not strong enough to pull the spike through a Lorentz factor of 1. You can't get these spikes. It's not strong enough to pull the pair bounce through a Lorentz factor of 1. It's not strong enough to create the spikes, and you will end the strong damping of the discharge, right? Right, so at this point, the electric field amplitude will change a little bit afterwards, and we'll discuss that change and what its implications for pulsar observations might be. But you won't get any more of this strong exponential damping. So the damping is pretty much done. Right, okay, so we can take a step back from the plasma physics and return to the actual pulsar. So, right, again, to look at the big picture, the oscillations in the pulsar polar cap are going to be a bit different in nature, but their amplitude evolution will be basically the same because they're controlled by the parallel dynamics. So we can take our physics intuition from the screening of the parallel electric field and apply it to the actual pulsar radio emission. So if I unnormalize everything, so I can balance the change in the pair Lorentz factor from the wave with the injected pair Lorentz factor, right? So here, this is a more realistic value for the lower energy pairs that are being dumped on the pair discharge in the polar cap. I can put in a value of frequency that corresponds to the frequency that you see in the radio. I'll also note that you can estimate that frequency from the plasma physics of the discharge and the temperature spread in the injected pairs, for instance. And you can look into that in our paper, but for here, I'll just say that this frequency is in the radio. And from there, you can get an electric field amplitude at which the strong damping of the discharge ceases. So if you take this electric field and consider emission at this amplitude across the polar cap, so if you square it and multiply it by polar cap area, you find that the amount of radiation that would escape is 10 to the 28 ergs per second, which is in fact consistent with the observed radio luminosity that we wanted to understand when we began this project. So this is very encouraging. All right, so I've just given you the simplest estimate of this effect that you can do. There are some kind of dependencies on this that relate to the actual more complicated physics of the discharge when you've got some structure in it, for instance, and that gives you a little bit of flexibility on the 10 to the 28th, which might explain the spread around this value that you see in the observations. This is exciting.
So it doesn't depend on the big gamma then?
Right, so the point at which this nonlinear damping stops does not depend on the big gamma at all. The big gamma determines how fast the damping happens, right, but not when it stops. So that's kind of cool because actually the dependence on overall pulsar parameters in this expression is smaller than you might expect. There are some dependencies, but it's not that great, or not that many.
You're saying that that number is roughly independent from the magnetic field strength then? Where would that happen?
Right, so there's a weak dependence on the magnetic field strength that comes from the size of the polar cap radius, right? You've got a lot of weak dependencies that come in through the size of the polar cap radius, right? And then you also, have other factors that come into play, like, what fraction of the polar cap is actually participating in this behavior. And there's some, expressions for that people have worked out. So you have a lot of sort of secondary dependencies, but the primary physics is not dependent on these things. Great. Okay, so after we complete the nonlinear damping, we're going to enter later phases of the discharge. So There's this phase 3, which I'll just call the frozen phase. This is when the amplitude of the oscillations is not going to change very much. This is actually an artifact of the simplified setup we've taken. And it won't occur in the actual polar discharge, and it will end it ends in our simulation when the discharge sort of breaks up into modes more similar to the actual polar cap modes. Right, so we can basically ignore this phase. I mean, it's not ignored in the paper, but we'll ignore it here. And after this phase ends, we'll enter the final important phase of the discharge, which is the linear phase, phase 4. So this is a phase in which the change in the newly added pair momentum is much less than the injection momentum. All right. Right, so this is the phase that sort of goes on until the discharge is fully complete. And you have to remember that as this is going on, you're going to continue to have the creation of new lower energy pairs, and the waves are going to continue to evolve due to this pair creation. But right, so this physics is going to occur across the polar cap for realistic electromagnetic waves. And later on in this discharge, you're going to start to get some of these waves that escape the plasma as Poynting flux and become the radio emission that we observe from pulsars. Right. So across the polar cap, this process of escape from plasma wave to light will occur at different points in the linear phase, at different points in this linear damping. And these will have different values of the electric field strength and of the frequency. Right. So you're going to get escape at different points during the linear phase, and these different points will have different values of electric field and frequency, and the relationship between these will give your spectrum, right? Because the idea is you got different things coming out, you see them all, and that gives you the spectrum. So this is a little bit hand wavy, this part. So this is, we're less confident in this than in the luminosity arguments, but it still gives us some insight. So again, the relationship between the electric field and the frequency is determined by this very familiar equation of blue. And the difference that we have in this phase compared to our nonlinear phase is that the frequency is not changing very strongly. You don't have these really dramatic spikes in the frequency that result from large displacements in the pair momenta as we had previously. So because the frequency is changing slowly, because the frequency is changing slowly, we can analyze this equation using techniques that are used across plasma physics when you have a plasma wave propagating in a slowly changing background. So these are WKB techniques, which you also know from your broader studies of physics. So basically, what you find here is that the relationship between the amplitude of the electric field squared is going to go like 1 over the frequency, right? So we can see this in our simulation at the left, or along the x-axis we have time, along the y-axis we have the strength of the electric field squared in the simulation box, right? So that the change in these big oscillations that go from 0.01 to 0 to this point where you just have a decrease without going to 0. This is because of this transition from the frozen phase to the linear phase, which you don't have to think about this if you don't want to, but if you're curious, basically what's happening is earlier on we have one electric field strength across the box, and then it gets fragmented into fluctuations with a low wave number. So it's not coherent across the whole box, and then you don't have the average in the box going to 0 anymore. But even though you have these low K modes, you can roughly analyze them using the 0K equation. You could also analyze them using the full equation, but that would be harder. But anyway, what you find is that if you compare this amplitude in the electric field squared to 1 over the frequency, you can do that in a dashed black line. And you find that indeed the amplitude of the radiation is evolving as we expect from our WKB intuition. So the idea is as this thing damps, it'll start to escape as light. And so this relationship, E squared goes like frequency to the -1, might be one of the contributors to the observed spectrum, which also has a spectral index of roughly the same magnitude. This is, again, kind of a hand waving argument. So there's a lot more physics going on that will give you the big scatter around -1.4, and also the difference between -1 and -1.4. All right, great. So this is about all I plan to discuss today. So basically, to recap what we've gone through, we've discussed how pulsar radio emission is a thing that's been known about for a very long time, but people still have a lot of questions about it. A couple of the things that they're interested in understanding is the radio luminosity and the radio spectrum. To understand these aspects, you have to know how the radio emission is generated. We discussed how it might be created by electric field screening in the polar cap of the pulsar. This is a complicated two-dimensional process, but it's ultimately controlled just by the damping of a parallel electric field, and that's a nice plasma physics problem that we've discussed in this talk. By looking at this plasma physics problem, we've shown that the radioluminosity of the overall emission might be understood as a transition from nonlinear to linear physics, from which we can work out a value for luminosity which agrees with observation. Then we've talked about some linear damping that happens later on in this discharge. And this might give you some of the behavior of the radio spectrum that you observe. All right, so this is based on a submitted paper, which you can all read if you have more you want to learn about, or we have actually a large amount of time for questions, so you can also ask me now.
Okay, thank you. Thank you, Livy.
Oh, Nadia raised her hand here. I don't know who.
Okay, let's give the approach to Nadia.
Yeah, I have a couple of questions. So one question was about those spikes and how much of an artifact. So exactly, well, you inject pairs with a certain velocity, and I wonder if in a more realistic situation where you have a spectrum of injected particles, presumably that might change qualitatively. So that was my first question, and then I'll ask my second question later.
Yeah, right. So in the simulation, I showed the injected momentum is basically 10, but in a realistic pulsar, my understanding is that value ranges between like 10 and 1,000, right? And it can also vary through the discharge, as you say. So that I think what that will do is that'll make the end of the nonlinear phase be some sort of kind of average of its value at all these different different injection momentums across the discharge, right? So it's going to be a lot kind of messier, but probably the actual physics is roughly given by the end of the nonlinear phase for an average pair injection momentum. All right.
Okay, thanks. Yeah, I mean, my second question was about just qualitatively, can you talk a little bit more about how exactly the emission leaves the cap? I think I understand in a sort of, you know, going from your one-dimensional picture to the three-dimensional realistic picture, but I want to hear about that a little more.
Yeah. So how does it escape, right? So if you look at the actual two-dimensional or really three-dimensional case, what you have in the realistic case is you've got electromagnetic plasma waves that are actually superluminal. So these waves move faster than the speed of light. So they're, you know, existing in a bunch of plasma that's moving basically at the speed of light. The waves go faster than the speed of light. So basically they're propagating through this plasma. And as they do this, they're going to go from the center of the plasma cloud to a region where there is no plasma. So that's a propagation of a plasma wave down a density gradient, right? From a lot of density to no density. And when a plasma wave propagates down a density gradient, it'll have some, you know, modification of its frequency and actually amplitude a little bit. as well from that density gradient. This might modify the spectrum a little bit. It's one thing we've sort of left for future work, but this physics is not supposed to be as severe, right? And as you go down the density gradient, as you go to 0, you actually leave as light. So that's how the emission leaves.
Okay,
So you explained some observation. I was wondering if you have some prediction of a different kind for future tests.
Some prediction of a different kind for so like something that people can use to like check our theory, right? So one of the things that you can make a prediction about is right. So one of the things that I've swept under the rug here is the dependence. Right. So this value of luminosity depends a little bit on the injected pair Lorentz factor, as Nadia was talking about, and also about the radius of the polar cap. And you can work out specifically the form of these dependencies, right? So for instance, one thing that you could do is you could check, is the weak dependence on polar cap radius parameters that you predict from this expression what you actually observe in observation. If you had some way of working out what the injected pair Lorentz factor is, you could also check that. I'm not sure if observationalists are able to determine what that is. So, yeah.
Patrick.
Yeah, so I was curious about where GR effects might enter this analysis.
Right.
So do you think that if this was done in a fully general relativistic context, there would be anything changing in your results?
So I think that there would. I am just not able to answer this question right now. I'll think about it more. I will actually look into this and write back to you.
Just effective frequency from range, because I mean the whole process would still proceed, but I guess just frequency would be to escape the gravitational tension.
And this you want to go ahead with the question?
I was just trying to say something on that question.
But you also had your own question. No?
I also had my own question. Yes, I had a brief question. More like on a technical point you mentioned, because you were just saying that the waves travel superluminally. I was just a bit confused. But that's
right. So this is a statement about the more realistic two-dimensional case, right? So in that case, if you work out the dispersion relation of the electromagnetic mode, you can find its phase velocity, and that's above the speed of light.
But that's fine.
Okay.
It doesn't mean that the information propagates.
No, it's not a group velocity. Sorry if I said that. That was incorrect. It's just, right, phase velocity. Yeah.
Actually.
So is this the only theory that can explain the radio emission from pulsars, or are there any other proposed theories that also try to explain it?
Yeah, right. So this is a subject with a kind of long and fraught history. There are other potential explanations. Some people think that this radio emission results from some sort of two-stream instability that exists in the polar cap region. Problem is, a two-stream instability is hard to get it to grow fast enough. Sometimes also people, think about, you might have these big bunches of charge that are all radiating together. That's not really clear how you get those big bunches of charge. Of course, I'm a bit biased because this was taught this way of explaining the radio emission. So I'm sure the people with those other explanations, I think there's a problem with this one.
More questions? Let's see if we got any questions on Zoom. I guess that's it. All right, so let's thank Liv again.